Good afternoon, everyone, and welcome to ISPE's quarterly webinar program. Today's presentation is ultra-white paints for full daytime sub-ambient radiative cooling, presented by Xiulin Ruan. My name is Emily Widener, ISPE's education specialist. I will be your moderator for today. I'd like to go over a few things before we begin. All attendees have been muted to avoid audio feedback issues. All questions will be held until the end of the presentation. To ask a question, please type it into the questions box and then we will get to the questions at the end of the presentation as time permits. The slides for this presentation can be found in the handout section of the toolbar. You're eligible to earn PDHs by logging into this webinar for its duration, and you'll be receiving an email later today with your certificate. With that, I will go ahead and hand everything over to Xiulin.
Sure, thank you very much, Emily. This is Xiulin Ruan. I'm a professor in the School of Mechanical Engineering and the Burke Nanotechnology Center at Purdue University. It's my great pleasure to be invited to this ISPE quarterly seminar. I really feel honored to do this and talk about our recent work on ultra-white paints for full daytime sub-ambient radio cooling. This has been a pretty fun journey for myself, and I hope you can see that this to be an interesting topic and something useful for our daily life as well as for our planet. Okay, let's take a look at what kind of motivated us to perform this research. You can see on this slide that numerous numbers of air conditioners are used worldwide. And these greatly really improve the quality of living for people. I would say air conditioner is one of the greatest inventions of our human history. So at the same time, when it cools down the space and make it more comfortable, at the same time, it creates a problem for the cities and our planet overall. So on the right, you can see a infrared image that shows the city center. I mean, the red color on the infrared image shows it's really hot. The city center can be quite a few degrees hotter than the surrounding rural areas. That kind of hot heat island effect will make our air conditioners less efficient, even consume more power to cool down the inner space of the buildings. All right, so with all the air conditioners used, it's a big sector of the energy usage, either commercial or residential. As you can see, it's responsible for 11% and 60% respectively. Moreover, not just electricity, they also account for 113.6 million metric tons of CO2 emission. So we are having the COP26 summit that all the leaders of the countries went to Europe to discuss our climate crisis. So this is really a timely topic that where we have to make timely actions for that crisis. Now, this is a map that shows the current status of air conditioners. The developed countries like United States, Japan, you can see already 90% or 89% of households already have air conditioners. So that really kind of speak for the quality of life. But even with this, the old units needs to be replaced with the new units of air conditioners. So but the other countries like China really picked up in the last decade or two. Now 60% of the households have air conditioners. But if you look at the other developing economies, like India, Brazil, Mexico, Indonesia, these are the countries with large populations. And we can imagine with their growth of economy and the people's desire to improve the quality of their life. So there's going to be huge growth in air conditioners. Now, there are like 1.5 billion air conditioners worldwide already used, but it's predicted by 2050, there might be 4.5 billion units air conditioners on the Earth. So they're gonna, a big eater for energy as well as create carbon dioxide emissions. So how can we do with it? So it has certainly very beneficial for our human beings, but one of the contributors to the climate problem, as well as energy problem. So we have been constantly reading the news that the different regions of the world are experiencing unusual weather, either extremely hot, extremely cold. But these can be largely due to the overall global warming trend of the Earth. So, like BBC News reported, Antarctica logs the highest temperature on record, meaning there are also news reports that the Arctic areas they were seeing the highest temperature on record also. And because of all those irregular weathers, and the polar bears are losing their homes, as you can see here, the poor polar bear. So what can we do about this? I mean, we have been looking at, in my group, have been looking at conventional air conditioning as the sector to see how we can save energy and help the climate crisis. So if you look closer into the air conditioning, you realize a few things. First, air conditioners use electricity, right? When they pump the heat from inside the house to the outside, you're moving heat from a low temperature place to a high temperature place. You have to use power to do that. It doesn't happen spontaneously. So we use electricity. 1 unit of electricity can move about 10 units. So when the coefficients of performance is 10, say. But that electricity usually comes from burning fuels in the power plants, right? They emit carbon dioxide. So that's one problem. Also, although the air conditioners, they can move the heat from inside the house to the outside, but the heat eventually still stays on the earth and it stays in the near ambient of the house. So it creates or contributes to the urban heat island effect, make the city center really hot. It doesn't go far, as well as eventually contributing to warming up our Earth overall, because the heat is still on the Earth. So we wonder if there's any way to really dump the heat to deep space, right? Let the heat leave off the Earth. And even a sweeter deal, can we do this for free? Okay. Well, our solution is radiative cooling. So what does it mean by radiative cooling? How does it work? Now, to see that, let's look at a very large system of the sun, the deep space, our atmosphere, and the Earth's surface, and see how the energy flow looks like and how we can cool surfaces by radiation. All right, first, the sun certainly shines the solar radiation to the Earth's surface. That solar radiation it includes a few different wavelength bands. We know it has UV, right? But UV is a small portion, 3.4% in the solar radiation. Although it's not a large portion for energy, but we know UV is harmful for our health. So that's why we need to apply sunscreen in the summer, so that it's usually based on titanium dioxide or zinc oxide. If you look at the ingredients in the sunscreens, those materials absorb UV, so the UV rays wouldn't penetrate and reach your skin surface. So okay, then the visible corresponds to 42% of energy. So the sun is pretty efficient emitting the visible light. I mean, it's a good light source for our daily activity. Interestingly, the sun also has a big fraction of energy that we cannot see with our naked eyes. That's called near IR or near infrared. Okay, that wavelength is longer than 700 nanometer or 0.7 micron. Okay, so when the wavelength is longer than that, we cannot see with our naked eye, but we can use certainly like infrared spectrometer or IR camera to see these radiations. So this is even more than half of the energy, is even more than the visible band. So this is a 54.6%, okay, a lot of heat. Now, this entire solar radiation is largely transparent to the atmosphere, so that's how it kind of gets through the atmosphere and arrive at the Earth's surface for the first place. And then the Earth's surface will either kind of reflect part of the solar radiation or absorb it, and different surfaces will kind of absorb or reflect different percentage of the irradiation. Okay, now another part of this, what the surface does, it actually emits energy on its own. So this is kind of many people are not aware of, or didn't realize, or didn't pay attention. You know, any surface, as long as the surface temperature is above the coldest temperature, which is absolute 0 degree Kelvin, they're always emitting energy, right? So like our human body, our body temperature is around 37 degrees Celsius, a little bit above room temperature, and we emit energy, infrared heat. So that's why the infrared thermometer, like forehead thermometer, can measure our body temperature, especially during this COVID era. That's a convenient way to measure temperature when you go to, like, you know, a clinic or so. The Earth's surface, they also emit energy. They emit different amount based on the so-called emissivity. If the emissivity is high, they're gonna emit more energy. If the emissivity is low, they're gonna emit less. But nevertheless, this emission is centered around a wavelength of 10 micron. Okay, around 10 micron, because temperature is so low, we cannot see these emission either. We have to use an infrared camera. But interestingly, from 8 micron to 13 micron, you know, that's a kind of a portion of this emission from the surface itself. Now, emission in this wavelength range, it is transparent to the atmosphere as well. Okay, this is a so-called sky window or transparent atmospheric window. Now, emission in this portion can go through the atmosphere as well and lose to deep space. So that allows a channel for our surface on the Earth to directly lose heat to the deep space without being interrupted by the atmosphere. Okay, that's really interesting. And the energy in this range is about 150 watts per meter square. It is much smaller than the solar irradiation, like in terms of per unit area, but this is a big number, you know, when you multiply the areas available on the Earth. We're gonna touch that a little bit later, all right? Okay, so how does radiative cooling works? Now imagine if you have a surface that you know, absorbs or emits very little in the solar radiation, which means that if it reflects nearly 100% of the solar irradiation, so the surface will not really be heated by the sunlight. Also, the reflected solar radiation is in the wavelengths from UV to visible to near IR, that is, can still largely go through the atmosphere and eventually you know, bounce back to the deep space. So it doesn't really warm up our atmosphere much either. So with high reflection to the solar irradiation, it really reduces the warming of our surface as well as reduce the you know, warming of our atmosphere. Okay. Now, if our surface can at the same time has high emissivity, then these 150 watts per meter square energy can be directly lost to the deep space through transmission through the atmosphere. Now, in this way, you can see our surface does not absorb any heat or nearly no heat from the sun, and it loses radiation of about 150 watts per meter square to the deep space. So overall, now our surface will lose heat, okay, by radiation, and it can be cooled below the ambient temperature, right? And once it's low enough, the ambient convection will heat up our surface once again and compensate or offset this radiative cooling and reach like a steady state temperature, but that is still below the ambient temperature. Okay, so this is how ambient below ambient radiative cooling works. So we need to find a material that can really reflect as much as possible of the sunlight and at the same time emit as much as possible in the IR. We need high emissivity in the mid IR and high reflectivity to the sunlight. Okay. All right, so this radiative cooling principle is not new. Actually, from centuries back, people in the ancient times, they knew to use this phenomena to make ice, actually. Right, this was an article from Scientific American in 1857. They told a story about how in the East Indies, people use this technique to make ice during nighttime. Okay, so this is a structure Asian people used. They put water in this structure, and when it faces the sky, when the sky is clear and the ambient is cool, but not necessarily below the freezing point. Even the ambient is above freezing point. Now the water will lose radiation to the deep space and cool several or up to 10 degrees below the ambient temperature. Now it can be below the freezing point. Ice will become, the water would become ice. So this was the way people make ice before the refrigerator was invented, in a certain climate. But works well for night, but during the day it doesn't work anymore because you see, these are not so white, so they're gonna absorb the sunlight, and the heating will be more than the radiation energy lost to the deep space. So the surface will be warmed up during daytime. So what can we do? How can we make something that work well during nighttime as well as during daytime? Because the daytime, when the sun rays are strong, is the time we need the cooling the most, right? In terms of air conditioning for buildings or so. Doing this radiative cooling has been pursued in modern era since 1960s, 70s, and people have really started with thinking about paints at the time. So this is the 1970s. You see the 1990s. People consider about the paint based on titanium dioxide. So this was a study that during nighttime it can cool below the ambient pretty well, but during daytime it still cool 2 degrees below the ambient. However, this study used the metal substrate as a high reflector to reflect sunlight. So if you use a paint alone, you won't be cool below the ambient temperature. In other words, it does not sort of demonstrate the independence of substrate. You have to use this on a metal to make it work. So which is not the case for buildings where we have concrete. Other formulas as well, they didn't sort of reflect sunlight well enough to really cool below the ambient temperature. So overall, the commercial white paints based on titanium dioxide, they reflect 80 to 90% of sunlight. So this number seems to be very high already. But when we think about absorption, these paints would absorb 10 to 20% of sunlight. Okay, that's a lot of absorption. That heating is more than the heat the surface will emit to the deep space. So we couldn't really see cooling below the ambient temperature under the strongest sunlight. Okay, in the just last few years, people look at other materials other than paints. For example, this is a very delicate nanostructure, multi-layer nanostructure. You see each layer has 230 nanometer or 20 nanometer or so. You have to control the nanometer, the layer thickness very well. This work was from the Stanford group. So with this structure, they were able to cool the surface below the ambient temperature, but it is very expensive. There's no way to scale this up and use for large areas like buildings or infrastructures, automobiles, and so on. Other approaches were also realized, such as this one is a silica mirror. It's a mirror coated with a polymer. Again, this is a rigid surface and cannot be used on surface with roughness or so. This thin film with a metal substrate, then we have polymer and the particles in it. The last one is a delignified wood that appear pretty white eventually. This wood needs to be very thick. It's kind of not convenient to use on the roofs or so. So there are limitations about these approaches, either too expensive, either they have metal We have to have the metal layer to reflect the sunlight. So that means that, again, can we make paints to do the same job, right? People try paints 1970s and it was not successful. Many people believe it was impossible to use paints to do this. Even when we started the work in about 7 years ago, we didn't believe paints were possible. We started with a two-layer structure. So this is where we started. At that time, we think that reflecting the sunlight needs to be done by one material, then emitting the infrared heat can be done by another material. So this is like a two-layer structure. All right, so when we designed this material, we started with a commercial paint material, titanium dioxide, to wonder that whether we can really use a commercial paint ingredient and to achieve radial cooling. And we use the prediction tools, which is something that we have to we can predict optical properties. Right now, for that, in principle, we need to solve the Maxwell's equations, but directly solving the equation for like a matrix with numerous particles in it will be too expensive. So we went with a multi-scale simulation approach that combining the scattering on each individual particle, we figure out the scattering coefficient and the fixed function asymmetric factor. Asymmetric factor means that once the light shines on a particle, what's the percentage that still travels forward and what's the percentage of photons that travel. So we prefer the backward scattering because that contributes to reflection, right? So with that information, we can put into a Monte Carlo simulation to really see how the photons will travel through this porous media, through this nano composite. And eventually the photons that are able to survive at the bottom surface is contact transmission. Those that are absorbed in between is absorption, and those bounce back to the top surface, that's the reflection. Okay, so we have this tool for design. Okay, I'll skip this slide. But so with those particle size, we can design and see how each different particle size behave. Particle size 0.1 micron, which means 100 nanometer, we can see it scatters about 0.5 micron wavelengths very well. So this is a scattering coefficient versus the wavelengths. Basically says how well the particle will scatter for different wavelengths. So the smallest particle here scatters very well, 0.5 micron. However, it quickly drops for larger wavelengths, which is not ideal because we know the sunlight has some of the longer wavelengths in it, and they contribute significantly to the heat from the sun. Now, when we increase the size, you can see 0.2, 0.4, 0.3. They start to reflect the longer wavelengths much better, but then we will sacrifice the shorter wavelengths. So none of these kind of a single size will be ideal because each wavelength, they really scatter, one or a neighborhood with one wavelength well, not the entire wavelength range in the sunlight. Okay. Now we can see the consequence on the reflectivity as well. For 0.1 micron, very good, near 0.5, but it quickly drops for longer wavelengths. Now we'll go to largest radius 0.4 micron. You can see it performance degrades in the shorter wavelengths, but it maintains a flat profile for a pretty broad range of wavelengths. Okay, so in other words, it reflects the different photons more uniformly. Okay, but when we go to the end, we know there are less energy in the solar spectrum, so it's complicated weighing or optimization how you're gonna, what particle size is the best to reflect the overall sunlight the best. But anyway, we designed our TiO2 based structure, and eventually we found the design that it can reflect 91% of sunlight. Okay, at the same time, the surface can have emissivity of 0.95 in the mid-IR, mid range of infrared, about 10 micron. So this is pretty good. I mean, if this performance is true, the absorbed sunlight, now in this case, will be 9%. When you reflect 91% of sunlight, you absorb 9% of sunlight. So absorbing 9% sunlight should barely make the surface to cool below the ambient, which means that the emitted heat can be barely higher than the absorbed heat from the sunlight. Okay, so we predicted the performance that when there is no convection load when in vacuum, say outside, when you do outdoor and putting things in vacuum, then you can cool the surface really a lot below the ambient temperature, can be 20-30 degrees. But when there is natural convection, say this will be windy weather, we can cool still up to 10 degrees Celsius, okay, or 18 degrees Fahrenheit below the ambient temperature. That's still significant. So at the same time, other groups tried the paint-like approach. This is a University of New Mexico group. They tried silica or silicon dioxide microsphere bed. They don't have any binders, so it's not really a paint. It's just a particle bed. So they were able to cool below the ambient temperature, when it is nighttime or even part of daytime. But during noon hours, around 12 p.m., you can see that the temperature of the sphere are higher than the ambient temperature. So although it's cooler than the commercial paint, so ambient is still the coolest. So it's not the full daytime cooling. The other approach done by a Columbia group, they demonstrated just pure polymer. They create a lot of pores in the polymer with a size about 6 to 10 micron pore size, and it works pretty well, cool below the ambient temperature. But the polymer needs to be pretty expensive in this case, in our design, and it needs to be thick coating to achieve below ambient temperature. So it's not a paint either. Now, when we look at our titanium dioxide paint, we did a study to measure the reflectance. So in this study, our experiment shows 90.1% reflectance, which is consistent with our prediction. But in this simulation, when the size is small, we only got like 84.2%. There's a fairly large discrepancy. By the way, this is a titanium dioxide rutile, the pigment used in commercial white paint. So when we look at the scanning electron microscope image, you realize that the particles, they do not really have a single uniform size. There's certainly some larger particle size, some smaller particle size, as you can see. So what we did is that let's see what's the impact of these non-uniform size. Okay, we measure that. It has a standard deviation of a 37 nanometer, and we find that after the simulation, we can agree with the results much better. I think I'm missing one overlay on this. So it does show that after you include the different size distribution, now the simulation can agree with the experiment very well. So the non-uniform particle size distribution is beneficial for achieving higher reflectance. Okay. Then we did a more systematic study using, say, if we want to optimize it to a single particle size, what would be the best? All right. We tried really tiny particle size, 25 nanometer to 50 to 100 and all the way up to 800 nanometer. Okay, these sizes are doable with commercial paints or with paints with a reasonable cost. So we can see that for the single size, 100 nanometer is the best performer to reflect the UV band, because the UV wavelength is small and you need a smaller particle to reflect those the best. Now, the best performer to reflect the visible band turns out to be 200 nanometer diameter. Okay. Now, if you want to reflect the near the best, then we need to use 400 nanometer, because near wavelengths are longer, then we should use larger particle to reflect that. And these 400 nanometer is also the overall best performer. I mean, when you add up all the different wavelength range, it reflects 87.9% if you use a single size. Okay. that now, okay, I think this is a slide. So with that, now we're able to show that with such distribution, we can achieve the better agreement with the experiment and show enhanced reflectance. Okay, now with that idea, kind of it stimulated us to intentionally design multiple particle size. So we came up with 4 designs. Design A include these diameters, and this is their volume fraction of each diameter. You can see the design D overall, I mean the particle sizes are larger, okay, 100, 200 to up to 600, and these are their volume percentage, right, of the designs. So we can see, you know, now compared to the single size are plotted as these dashed lines or dashed dot lines, and A, B, C, D. If we zoom in, you know, the performance, we can see the A, B, C, D designs, they show a more uniform reflectance across the wavelength range. Now we zoom in the UV portion. You can see the UV portion, the design D is the best. Okay, design D is the best, although they are better than the other single size. Okay, when we go to the peak portion, we can see the D design is pretty good in the short wavelength range, and it maintains almost flat. You know, which means that it has high reflectance nearly for all the wavelengths. Although at the longer wavelengths, it start to be below the another design, which is design C. Okay, design C is better in this region. Okay, but we will see that it turns out the overall scattering to the sunlight is the best. When we look at design A, B, C, we can see A is the best for the UV, B is the best to reflect the visible, C is the best to reflect the near. Design D also is the best overall, but is not a winner for any of the individual band, which is interesting. Which means that just like a sports, right? If you need to participate in multiple activities, you may not be the best in each one, but your total score might be the best. So this is what happens to design D. Design D is a balanced design that it does fairly well, not necessarily the best for each band, but overall is a winner. Okay, so that's an interesting finding that indeed for our design we need to prefer the multiple particle size. Okay, so with that in our mind, I mean we had to design field test setup. So we have 2 setup. One is you put the sample just under the sun, and to sort of mitigate the different wind speed at different time, we kind of shield the sample from the wind, I mean, to get a more rigorous scientific study. And in other tests, we sometimes remove the shield actually to let the wind come in to be more like realistic cases. So we have done both. So in this case, we just let the sample face the sky and measure temperature, and to see whether the temperature will be below the ambient temperature, okay, to show the cooling. In another design, we try to measure the cooling power. So in this test, now we put a feedback heater at the back, and we adjust the power of the heater so that the sample temperature is always the same as ambient. Okay, so in that case, we eliminate any heat load from the convection, and all the heat generated by our heater that goes to the sample is lost through radiation to the deep space. So when we sync the temperature to the ambient, then the heater power is the same as the cooling power provided by the sample. Okay, so one setup is to measure temperature and confirm it can be cooled below the ambient temperature. The other setup is to measure how much cooling power we have for the system. Okay, so we did this for our TiO2 material. As you can see, we got very good below ambient cooling temperature during nighttime. The ambient is here, and our surface temperature is here. It's kind of 10 degrees below the ambient temperature. But during the daytime, when the ambient temperature is here, our TiO2 is a few degrees above the ambient temperature. So we don't have net cooling below the ambient, still slightly warmer than the ambient. But it is kind of cooler than the other darker color surfaces. Here is a carbon black. Carbon black, we know it absorbs sunlight strongly, and the kind of temperature shoots up to be really high. I mean, this kind of mimics some of the black roofs. They absorb a lot of sunlight, and that turns into heat, the dump into the ambient, and heat up the earth, as well as eat our air conditioning power to cool our house. All right, so the reason for the TiO2 is that it kind of we know the TiO2 is part of the sunscreen ingredient. It absorbs the UV portion. Okay, that's part of the energy. And how can we do better than the TiO2? So again, this goes to the band gap a little bit. We know that TiO2, the band gap is a quantity that says if the photon energy is above the band gap, it will be absorbed. So this is for TiO2. For a photon from the sunlight in the UV portion, it can excite electron and let it excite to the conduction band. So the photons will be absorbed and contributed to heating. Okay, so to minimize the solar absorption, we need to see alternative materials with large electron band gap. So the photons do not have enough energy to excite electrons. For example, calcite is a material like that. As you can see, there's a very large gap. And when a photon comes in, try to excite this electron, the energy is not enough to make that transition. So this photon will be bounced back without being absorbed. Okay, so this is a better material in terms of reflect the sunlight and not absorb. And we have a few materials with that characteristics. You can see zinc sulfur band gap is higher, and then alumina, barium sulfate, and calcite. So our team really focused on the last two materials, calcite. We realize the performance first, and then barium sulfate. Okay, let's see how they work. So when we put the calcite particles into the acrylic matrix and mix them well, let them dry, and we eventually achieve very nice cooling capability. Now, this is a calcite painted surface versus commercial paint. They look white. It's hard to show the difference in on a computer screen, but if you hold the two painted plates, you can tell actually our calcite is somewhat wider than the commercial. Okay. Because it increased the reflection from 80% or to 90% to 95.5% for our calcite paint. So it kind of whiteness, actually enhancement is not that huge. If you think about from 80 to 90% to 95%, right? It's not a large enhancement. But for the energy point of view, we need to think about the absorption, right? For the commercial paint, they absorb 10 to 20%. Now our calcite paint absorbs 4.5%. So that cut the heating by at least 2 times or to 4 times, right? That's a big deal. That's much more reduction than the enhancement in the whiteness of the paint. That's why it's just kind of a little bit wider than the commercial white paint, but it has a huge impact on the energy on the heating side. Nevertheless, you can see our calcite size is a kind of pretty broad. And it has a nanorod kind of structure. It's about 1.7 micron long and 500 nanometer in the diameter, right? Emissivity is high as well, 0.94. So eventually the immediate energy is way higher than the absorbed energy from the sun, and we can achieve below the ambient cooling. Now, again, there are a few key innovations. We use a material that with a large band gap to not absorb the sunlight. We use a high particle concentration in order to scatter, most sunlight as possible. Then the broad distribution of particle size will help scatter and reflect all the wavelengths in the solar spectrum. So all the 3 factors are important to achieve the such wide paints. If you miss one of them, that's kind of happens in the commercial paint. You will not achieve such high reflectance. Okay, so this is a full daytime sub-ambient cooling we demonstrated. These are the sketches I already talked. So you can see we kind of monitor the temperature of the ambient or our paint during nighttime, it cools more than 10 degrees Celsius below the ambient. And even during the strong sunlight around noon hours, our calcite is still about 1.5 degrees Celsius below the ambient temperature. And the cooling power is about 50 watts per meter square for calcite, right? Through the 24-hour range. Although during nighttime is higher than that number, during noon hours is smaller than the average, but it's still a good amount. Now, this is an intuitive way to demonstrate the cooling effect. We painted this P pattern with our calcite paint and all the rest background with commercial paint, right? So with the naked eye, you can see our P is a little bit wider than the background, but under thermal camera, the P pattern is much cooler, showing the below ambient cooling effect. Now, this is even a better formula after we demonstrated the calcite. So the barium sulfate particles, they have a little bit smaller band gap, so they provide a slightly higher Riffer index, which helps the scattering. And with this formula now, it can reflect 98.1% of sunlight. That's kind of the record high reflectance to the sunlight among all the paints known to us. At the same time, it has an emissivity of a 96%. So in this way, our barium sulfate paint only absorbs 1.9% of sunlight. That's almost nothing, which means it doesn't matter nighttime or daytime. When you put this painted surface outside, it is idle to the sun. It absorbs almost no heat from the sun at all, while emitting this infrared heat to the ambient. So we're able to now achieve about 4.5 degrees Celsius during the strongest sunshine, or about 8 degrees Fahrenheit below the ambient temperature. The cooling power provided by this painted surface on the order of 100 watts per meter square. Okay, so this is significant because we don't use any power. You just paint your roof with this, and think about a 1,000 square feet, one-story house. That's nearly 100 meters square. So multiply by 100 watts per meter square cooling power. So for that, a house with a normal size, the radiative cooling will provide about 10 kilowatt cooling power from the roof. Okay, that's a lot of cooling power just by one house, and that really helps cooling down the earth, and also helps saving the air conditioning. So you can imagine that when we apply those to many roofs, and it really a lot of cooling power for our planet, because that heat, all the reflected sunlight and the emitted infrared heat goes to the deep space, not stay on the earth anymore, right? It cools down our earth, not even like a stop the warming. Stop warming is good, but our paint really cools the earth down. I mean, pull the temperature back to decades ago when the earth was cooler. Okay, so this figure shows benefits of different particle size. We have done systematic study, the higher concentration are better, and also the multiple size are better. You can see this is a single size with 90 with 60%, and only when we do a multiple particle size, it can give us a few percent more. Each 1% enhancement in the solar reflectance corresponds to 10 watts per meter square less heating. So every 1% enhancement in reflecting the sunlight is worth doing, as long as the cost is reasonable in that sense. Okay, I'll skip this slide. So we know our work would make some good impact, but it's really to our pleasant surprise to capture so much attention. It's covered by almost all the top news media globally, such as BBC. They covered twice when we have had this calcite and barium sulfate formula respectively. CNN, the Washington Post, Wall Street Journal, and recently USA Today, and even featured in talk shows like Jimmy Fallon's, Stephen Colbert, and the SNL more recently, and globally in different languages. This is a local printed Indian newspaper. Somebody forwarded this to us So good to see that in Spanish language, Korean, China, Japan, and so on. So we have numerous inquiries about the paint when it become commercially available. So we're working with a large company towards commercializing this technology. We need to do more testing to make sure it's kind of reliable over long term. We hope it can last at least similar lifespan with the commercial white paints, 5 to 10 years ideally, and optimize the formula before we push to the market. So yeah, here I think this is one of the last slides I have. So we did analyze the energy saving for buildings. So many people say that our paint can this replace air conditioners. Well, in some locations, hot weather, the cooling may totally remove the need for air conditioning. However, for the deep south region of the United States or like the Middle East and India or so, the paint alone wouldn't bring the temperature down to the comfort level in the hottest summer days. So actually our paint can work together with air conditioners, so it can be used as a pre-cooling unit, meaning so the air is cooled by radiative cooling first, then intake by air conditioner. So when the air conditioner take in the air is already cooled down, so that less electricity will be used to cool it further to the set point of the house. Okay, so we have done these different roof coverage of this paint, and the baseline is without radiative cooling at all, and then these RC and the CRC are two different types of implementation of our radiative cooling system. You can see electricity use is cut a lot by this. This is in collaboration with Professor Jim Brown in ME, Horton, and PhD student Yu Hong there, but done by my PhD student Joe Peoples. Okay, so this is a figure showing the energy saving. You can see the savings can be up to 75% or even 80%, depending on how much you cover your roof. This is in Reno, this is in Phoenix. They show similar amount of energy saving for the summer months. Okay, so that's for individual house. Then if we look at the Earth scale, based on the model provided by Professor Jeremy Manda from the University of California at Davis, and plugging the performance of our paint, you can see the sun shines light on the Earth will lose heat by radiation, so eventually reach a balance. So the Earth is at a very good distance from the sun, so that eventually it arrive at the suitable temperature for liquid water to exist. I mean, for lives to exist on the Earth. Now the Earth is being warmed up because the heating is more than the cooling. But if we apply less than 1%, well, if we cover less than 1% of the Earth's surface with our paint, we should be able to totally stop the warming trend and cool this back by 1 to 1.5 degrees. Okay, which means that warming Earth plus 1% of the paint, no matter its roof, roads, cars, and so on, we are able to cool back. But we cannot do too much, right? If we do 5% or 10%, it will overcool the Earth, make it like maybe an ice planet, which we don't want to do that too. So less than 1% is about right. Okay, so some future opportunities in the cooling paints. Right now, quite a few students in my group are working on different aspects, and we are also working with our industry partner towards commercializing this. But a few developments are also underway. For example, how can we search for better materials? I mean, so far these materials are trial and error, and we want to make it predictive, and even use some inspiration from biology world. Use machine learning to find the best material and the systems. And the color paints, right? Many people maybe not like a white roof, although New York City, Los Angeles, there are a lot of buildings already very white. I mean, they're doing pioneer projects to add more white surface to the roofs or cool roof pioneer project. In New York, they're doing 10 million square feet cool roof or white roof. But for people who like color, can we, based on our white paints, to add the color ingredients but still preserve a lot of these cooling benefits. I mean, that's doable actually, so this is underway. And other aspects like advanced manufacturing, reliability of this paints, analyze energy savings for different climates so far is the most beneficial for the hot climate. But even for cold climate, Arctic area, people have talked to me, although they are very cold, I mean, but they see the danger of melting the ice. So even that area, you know, putting a white roof will be very beneficial to preserve the sea ice and to bring back the habitats for polar bears and so on. Okay, so that's kind of larger scale. How do we understand the climate impact of these? I mean, we cannot apply that 1% just on one place, but it has to be distributed. Okay, so I mentioned the Scientific American article earlier back in 1850s, but this is a new coverage of our story, so nicely done by Scientific American. See how this can be combat climate change. Now, this is my group of students, a little bit outdated. I mean, we have a few more students joining who work on this new project as well. And I would like to acknowledge the people who graduate from my group, my collaborators and current students, as well as funding sponsors to make this work possible. Okay, I think that's all my talk today. Thank you very much, and we'll welcome any questions.
Great. It looks like we do have one question. Like I said at the beginning, if you have any questions, please put it in the questions box. The question is, normally when dealing with solar radiation, surfaces on the Earth are modeled as exchanging radiation with an idealized black surface at the effective sky temperature. Is it reasonable to say that treating the surface essentially makes the effective sky temperature significantly smaller? Or is this effect already taken into account with low values of total solar absorptivity and high values of total emissivity?
Yeah, that's a great question. So for the typical Earth surface, they absorb 70% of the sunlight. And the emissivity is about 98%. So I mean, the Earth surface actually they emit pretty well. So now with our paint, actually we are really not the best experts to model the impact of climate, how this gonna exactly impact climate. So that's why I put the climate impact as one of the future directions. We're collaborating right now with climate scientists to understand that. I mean, it's good to know that this year's Nobel Prize in Physics was awarded to a few scientists who developed those very complicated climate model. So my understanding is that now our surface, our whitest paint only absorbs 2%, less than 2% actually, of the sunlight. So yeah, that means that less. The Earth's surface will be heated less by the sun. At the same time, it should indirectly cool down our atmosphere as well, because the reflected energy will go through the atmosphere and are lost. So yeah, we haven't done that model yet on how this will exactly impact our atmosphere temperature. But my sense is that since the Earth's surface temperature will be reduced with the paint, the atmosphere temperature will be reduced as well. I mean, the other aspect is when the Earth emit heat to the outside with our paint, the Earth will emit less heat as well. So the CO2 in turn in the atmosphere will trap less heat from the Earth's surface. But we're not talking about a large temperature change after the paint. If we apply 1%, we may cool the Earth's surface by 1 to 1.5 degrees Celsius. So you may cool down the atmosphere by a similar amount as well. Yeah. So that's my understanding now. We may have better numbers to share in the future. Thank you. It's a great question.
Yeah, and it looks like we have some more questions coming in. The next one, for how long do these paints retain their properties? Can they be cleaned?
Yeah, that's a good question too. Right now we have done like a short-term testing for outdoor, say a few months. It doesn't change the property at all. We have done extended the UV exposure when it is exposed to UV for similar to commercial paint, it retains the property. I think now the remaining question for us is that how often you need to clean it. So we are looking at the ways to put the coat, to make sure the surface is hydrophobic, so that the rains or dust will roll off when there is rain, or it's a kind of self-clean property. So that we don't know yet, but we're confident to say that with some more optimization and testing, we hope that our ultra white paint will maintain clean as long as the other commercial white paint. So with the hydrophobic, it should be easy to clean off the dust on it as well.
What happens to performance as the paints become dirty in open air?
Yeah, well, if it does become dirty, it will lose some of the high reflectance, right? When it's dirty, it may become similar with commercial paint, and when it gets really dirty, you start to absorb even more and behave similar with some the other darker surfaces. Again, we are working on to make sure that it will be maintained clean as long as it can, and it is easy to wash if we need. But anyway, if we compare to commercial white paint, the good thing is that our paint does not really incur additional cost. The material barium sulfate is actually even cheaper than titanium dioxide. So we talked to a few mining companies, meaning they were pretty optimistic on the mining the barium sulfate. It is safe as well, although barium is a heavy metal, but it's not, the barium sulfate is not insoluble. It's not soluble in water. So during medical tests, you can even swallow this compound. But back to that, our paint will be anyway. Even consider it may get dirty, but it should be better in the commercial white paint. For at the same conditions.
Has your team looked at surfaces other than roofs? Parking lots came to mind.
Yeah, so exactly. We are looking at the parking lots and the roads and the automobiles. Yeah, we are in discussion with a few leading automobile companies because all the companies are aiming for more sustainability and saving the AC cost. So for electric cars, actually, if you can reduce the AC, it help on the driving range. So it definitely reduce the anxiety for the driving range. Now, each car, the area is not large, but if you can't add up all the cars currently in operation, that's a very large area in total. So yeah, these are some applications. There are other especially like a metal roof or mobile houses. They do not have insulation. Those are great application cases for this cooling, because that's gonna really reduce their heating by a very large amount.
Okay, the next question, will this increase the heating requirement for buildings during heating season?
Yeah, so that's a good question too. In the north, in the very deep north, you do maybe see some penalty, but in most of the climates, even for the cool climates, it should help. The cooling is more needed, considering some internal appliances, internal heating used in houses. I mean, we need definitely cooling more than the heating in most of the climate in the US and in the world.
Okay, this is going to be our final question. Could this material be incorporated into pliable roofing materials?
Yes. So this material needs to be applied on the top of the roofing shingles or so. I think we are also in discussion with these companies that you cannot put this inside. This coating or paint needs to be face the sky so that it will function for its best functionality.
Okay, it looks like that's all the questions we have. If you guys have any more questions, Xiulin did have his contact info on the first slide, and you do have the handouts available to you. Or you can reach out to me and I can direct them to him. You'll be receiving your certificate via email after the webinar is over. Thank you everyone for joining, and thank you to our speaker and taking time out of his day for a great presentation. So have a great rest of your week, everyone.
Sure. Thank you very much for your interest, and thank you again for inviting me to join this great event. Yep. Bye. Have a great day.